So let's talk about merge sort slash recursion. So we'll wrap up some sorting and some runtime analysis stuff, and the end goal is going to be to write recursive methods in this case. So our objective here is to write a recursive method, and we're doing this by adding our new restriction for functional programming. Why is this so loud? Adding our new restriction for functional programming. This will be the restriction that we see today for today's lecture question, for the next 4 lecture questions, and for the next round of homework assignments for the functional programming homework assignments. Is we're banning var. You can't change the value stored in a variable. You have to use val to create a constant and not change that value that's stored in there. So the intent is to use a recursive solution for this. And what we're doing is something pretty straightforward, because we want to focus on the recursion, not the problem itself for this, is compute the nth Fibonacci number. If you haven't heard of Fibonacci numbers before, it's a sequence that starts with 1, then 1, and then each number after that is the sum of the 2 previous numbers. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on and so forth. And our indexing will start at 1, so fib of 1 is 1, fib of 2 is 1, and then after that it's the rest of the sequence. So with this, we would naturally think of an iterative solution. We would write a loop to sum up the values and then return that value, except you need a var for that. So that would be our typical accumulator pattern from 115. Create a variable that's going to accumulate all your values, sum up all those values, and then return whatever you computed. So we can't do that anymore with var being banned. So we want to use that recursive solution. I want to push you to the functional programming way of thinking, just like I banned control flow to push you to the object-oriented programming way of thinking. So how do we solve this in a recursive way? How do we write a recursive method that's going to solve this problem, this Fibonacci sequence problem? So let's talk about it, but let's wrap up some runtime analysis and our last bit of sorting before we dive into that. So with runtime analysis, we have this question of how efficient is an algorithm, or how efficient is a method or a function? How efficient are these? I'll usually say algorithm here. But how efficient is an algorithm? How long does it take to run? Like that. These are our questions. This is what we want to solve. And we're going to solve that using asymptotic analysis with big O notation. And specifically, we're going to count the number of steps taken in an algorithm. And step is kind of ambiguous. So is basic operator. But I'll say how many basic operators are executed during the runtime of the algorithm. And we'll say those are like addition, subtraction, Boolean and, multiplication, any basic operation that's going to go to our processor and be processed in constant time. So how many steps does an algorithm take? And then where it becomes asymptotic is what's the rate of growth of the number of steps of an algorithm in terms of the size of the input. So how long does it take in that sense? What's that rate of growth in the size of the input? So for some input of size n, which is typically the number of elements in our data structure when we're talking about data structure, when we're talking about sorting, when you talk about data structures next semester, it's going to be the number of elements in that data structure. And we want to measure the rate of growth in that terms of that. So how does the runtime grow as the size of the input grows? And we want to ignore constants in lower order terms when we're computing this big O notation. So if this runtime grows linearly in the size of n, we're going to call that big O of n, which means that the actual total number of steps is some constant times n, and then possibly plus some lower order terms. So we might have 1 billion times n plus 1 million, or we might have n divided by 1 trillion as our actual total number of steps. Both of those are going to be O of n. We don't care about those constants in asymptotics. The idea behind this is we're concerned with what happens when the inputs get extremely large. What's our runtime going to be at those very large values? With very large values, even if we have a runtime that's 1,000 times n or just n, versus those can be considered fairly close to each other compared to an n squared algorithm. So what happens when our input is 1,000,000? I'm going to take 1,000 times n over n squared any day. When I have 1,000,000 times 1,000,000 over here, and I have 1,000 times 1,000,000 over here, I'm going to take 1,000 times 1,000,000 every day. Of course, I'd like the just linearly n, just n runtime, but I'm going to take n times 1,000 over n squared if my inputs are getting large. And that's what we're concerned with algorithm design, is what happens when our inputs are large. Because if our inputs are not large, well, why are we even using a computer? Like we use computers because we have lots of information, lots of data to work with. We have a lot of numbers to crunch. If our inputs aren't large, maybe there's another solution. Certainly not a design a very sophisticated algorithm solution. We would just use whatever first approach we had to be able to solve a question. This runtime analysis, we'll do a quick couple of them here, and I'll be a bit hand-wavy with it. I'll kind of skip some steps and not be too detailed. And you've seen this stuff very, very briefly in 115. You'll see it briefly again this semester, but I guarantee you in CC 250 you'll get a healthy dose of runtime analysis. 250 is pretty much all about runtime analysis. How do we design and build data structures to be able to decrease our asymptotic runtimes and get the most efficient runtimes out of our data structures for our particular applications. The 250 is pretty much the runtime analysis class, and then how do we get our data structures to get the most optimal runtimes, analyze those runtimes, and prove that those actually are the runtimes that we're getting. So for today, it's still just another taste of it, just like the taste you got in 115. So with that in mind, let's take a look at our selection sort and take a look at the runtime of this. And we want to count the number of steps, but we're going to count them asymptotically. So as long as we can get the right order of magnitude, the right rate of growth, we're going to be okay. So is this n or n squared or n log n? We want to figure out the right rate of growth. And the constants we're not going to matter. We're not going to be too concerned about. So let's look at this outer loop first. We have our input data, which is going to have some size, and that's going to be our n for this case. However many elements are in that list, that's our n. And this outer loop is going to iterate over the indices of that input. Since we're iterating over the indices of the input, we're going to run this loop exactly n times. There's no asymptotics, there's no constants in this one. There's exactly n times, which of course is O of n. So this loop runs O of n times, and then we want to compute the runtime of everything inside the loop, and we're going to multiply those runtimes together. So however long it takes to execute everything inside this loop, we'll have one runtime, then we have to multiply that by O of n to get the overall runtime of this outer loop, which is the runtime of the entire loop, the entire algorithm. So everything outside this inner for loop is going to run in faster than the for loop, I'll say. It runs linearly, but we're really concerned about this for loop because this is where our runtime can really blow up. So how many times does this for loop run? It's very easy to just say, well, O of n, because this loop runs I to data.size, I can be 0, and this is n, that's going to run n times. So it's easy to just say, well, in the worst case, it's going to run n times, which we're always concerned about worst case analysis, so therefore it's O of n. We're actually going to arrive at that conclusion, but we have to be a little more careful about it. We can't just say, well, worst case, therefore. Because when I is n over 2, this is only going to run n over 2 times when I is, which is still linearly in n. But what happens when I is log of n, which it's going to be at some point, log of n, n over log of n technically. This is only going to run log of n times. So how do we actually say that? For now, I'm just going to say, well, let's just say it's O of n, and then in a few slides I'll show some math that shows that we really do get the runtime that we arrive at. So if this is O of n, and our outer loop is O of n, so this loop runs O of n times, and that loop is being executed O of n times, we end up with our overall O of n squared runtime. So we got our O of n squared runtime for selection sort. Kind of. Except I'm being very sloppy with my algorithm, and actually have this data.apply inside that innermost loop. Well, data.apply of j is going to run it's going to take O of j time J is going to be O of n, so this is going to have O of n runtime, which is going to blow up my runtime to n cubed for this case. This is an instance where we can have an implementation of an algorithm that's actually slower than the algorithm should be in theory. So in theory, theoretically, selection sort is an n squared algorithm, but my implementation is so poor that I actually get an n cubed algorithm. And the reason I do this is so when we talk about linked lists, this has a big blow up because it's based on a linked list. We're getting the jth element of linked list, we have to hop a bunch of references to get there. And I do this because when I talk about linked lists, I want to say, hey, remember when we did that thing and we had that n cubed? I want to flash this back and say, start talking about why we get an n cubed runtime out of this. So keep that in mind. Choosing the right data structure and using the right data structures properly is going to be crucial to actually writing efficient software, which again, 250 is going to really talk about that all semester. So let's talk about that runtime of that inner loop. I just said, yeah, it's probably O of n, that's fine. But let's actually look at the number of times that inner loop is executed in a more mathematical way. So the first time we reach that inner loop, we're going to run it n times. The very first time we get here, I is going to be 0. So 0 until n is going to be exactly n times. And the next time we reach there is going to be n minus 1 iterations of that loop. The next time we get there is n minus 2 iterations of that loop as I is incrementing. So on and so forth until we get 2 and then finally 1 iterations of that loop. If we sum all this up, this is going to be n squared over 2 plus n over 2. And when we're talking about asymptotics, we're ignoring all constants, we're ignoring all lower order terms. We're just concerned of the highest order term without any constants, which is this n squared. Everything else we don't care about in asymptotics. So we get our O of n squared runtime out of this thing. So even when we unfold this sequence, once we unfold this and compute the sum, we do see that it is actually an n squared. We didn't just make that up, that, oh, worst case kind of hand-wavy thing. We actually do get a legitimate n squared runtime when you're computing a geometric sum like that. So we get an n squared runtime out of selection sort, and then n cubed, my crappy implementation, that inner loop is actually taking linear time. We can do similar math, that inner loop, that apply of j is going to have a similar summation. We're going to get up to that n cubed. So let's do better. So let's introduce merge sort and see how we can get down to n log n. You saw in 115 that this is n log n. Very brief explanation of why it's n log n. So let's talk about this a little more, and then finally we'll shift into the recursive part of this. Merge sort does use recursion, and that's where we want to shift our focus moving forward, is how did that recursion work and how do we write recursive algorithms and recursive methods eventually. So merge sort, the algorithm, can fit in a slide. If the input is less than 2 elements, just return it. There's no work to be done. This is what we call the base case of our recursion. And then if it's not the base case, we're going to hit our recursive case, divide the input list in 2 halves, and sort each half using merge sort itself. So use the algorithm that we're currently writing to sort these, and then merge the 2 sorted lists together in a single sorted list, and then return that list with those elements in it. So let's see this visually. If I want to sort this list that's conveniently 8 elements, a power of 2, so it looks pretty on a slide. I have this list of 8 elements. I'm going to call merge sort, and merge sort is going to say, does this have less than 2 elements in it? The answer is certainly false. So it's going to split that in half. It's going to split the list in half and recursively call merge sort itself on each half of the list. Each half is going to run the same exact algorithm. It's going to say, is the size of this list less than 2? No, 4 is not less than 2. So the algorithm is going to go to its recursive step, recursively call itself on each half of that list. Same thing here, 2 is not less than 2, so recursively call itself on each half of the list until we get down to these base cases. We're going to make all those recursive calls down to those base cases. Once we've reached the base case, the algorithm can finally start returning. So The input is 51. Is the length of this less than 2? Yes, 1 is finally less than 2. So we just get to return 51. Is the length of this less than 2? Sure, return it. And now this recursive call gets the return values of these two recursive calls and has the task of merging these two lists together. And I didn't show the algorithm for merge yet. We'll talk about that one in a few slides. How do we merge these two lists? So I have to merge these, and this recursive call has to make sure that the 1 is going before the 51. This recursive call gets these two return values and make sure the 19 is going before the 100. And then this recursive call is going to get these two return values back, get these two lists of size 2 that it has to merge. And this list has a little more work to do. It has to make sure the 1 goes in the right spot, the 19, the 51, and the 100. And then finally, this one's going to return with the same stuff happening on the other side. These two recursive calls are going to return, and our top level recursive call has to merge those two lists together to get the final list that we're going to return. And we use recursion for that. So in the code, is the list length of the list less than 2? If it is, just return it. Else, split this thing in half. And here I'm actually taking advantage of integer division. This is one case where we want integer division. I'm taking the length and dividing it by 2. And if the length is odd, so if I have a length of 9, I don't want 4.5 as my midpoint. I can't use that as an index in my list. So I'm taking advantage of that, and that would return 4 in that example. I'm calling this split at method, which is going to divide a list, given an index, split it on that index. That returns 2 values, so I'm using a little extra syntax here to get those that division, and getting the left half, which is everything up to but not including the midpoint, and then the right half, which is everything after that that midpoint and beyond. So if our list is of size 9, left has the first 4 elements, and right has the last 5 elements. So I don't have to worry about this odd and even thing. I'm just going to split using integer division, and that'll take care of my odd and evens. Make these recursive calls on the left and right hand side. I get a comparator for this, so we're using the same idea with the comparator with the function as a parameter and the type parameter that we saw on Monday with selection sort. And I'm just giving this comparator to my recursive calls. I'm assuming the recursive calls are fine, and then I'm left with the task of merging those two lists using that same comparator. So the next question we want to ask in terms of runtime is, how much recursion do we have? That's awkwardly worded, but when I'm splitting this list down into the recursive calls, how far down do I have to go to get to my base case? So if I visualize it like this in what we call a recursive tree, and think of each one of these as a layer to the tree, how many layers am I going to have in my recursion? So at this one, I have 8 elements, and in my first layer, I have 2 recursive calls of size 4. In my next layer, I have 4 recursive calls of size 2. And in my next layer, I have 8 recursive calls of size 1, and I've reached my base case when I get to this layer, when I get to layer 3. So my question is, in general, how many layers does it take to get to the base case? So we can observe that at layer I, my inputs are going to be of size n over 2 to the I. I'm splitting my inputs in half each layer. So if I go 3 layers, I just cut my inputs by 8 and reach our base case in our example case. In general, we want to ask ourselves, when is n over 2 to the I equal to the size of our base case? And if we solve this for I, we're going to find I is log of n. So we have log of n levels to this recursion. And if our goal is n log n runtime, our new task is to be able to do that merge step in linear time. If we can merge in linear time, we'll actually reach our n log n. So as long as we can merge in linear time, we're good to go on that. And this is where we start to see the power of exponentiation and logarithms. These are 2 very powerful concepts, especially in computer science, when we're writing algorithms whose runtime can depend on these. The log of n, we don't really get to see the power of this when our input is size 8 in the slides. With 8, the recursion, it took 3 levels to get down to our base case. But logarithm grows extremely slowly. If our input was size 1,000,000, how many layers would it take to get down to our base case? How many times do we have to break 1,000,000 in half to get down to 1? It's only 20. It would only be 20 layers to our recursion to get down to that. If it's 1,000,000,000, it's only going to take 30 layers to get down to our base case. This logarithm and exponential growth, these are extremely powerful, and they can work against you. If you have an exponential runtime, that's prohibitively useless. Like, that's not an algorithm you can really use if you have exponential growth. Exponential growth, it's something that's kind of taken over by pop culture a little bit. You hear that a bit out there when things are actually not exponential growth. When we say in computer science, we really mean exponential growth, and it's a ridiculously fast growth. It's a very fast one. We're usually talking about twos, like powers of twos as well. 2 to the, just the reverse of the examples I gave, 2 to the 30, if you take 1 and double it 30 times, you're at 1,000,000,000 already. It's very, very fast growth. But when we're talking about logs, the difference between n log n and n squared is a huge difference, especially as your inputs grow in size. So our task is to merge 2 lists in linear time. A quick overview of how we're going to do this, because of course we're going to accomplish this, or else it wouldn't be in these slides. We'd be talking about a different algorithm. So we want to merge 2 lists. What we're going to do is start by looking at the first element of each list. We're going to compare those 2 elements, and whichever one comes first, that's the one we're going to copy to an output list, and then advance that pointer. We're going to keep comparing the 2 values that the pointers are looking at, and take whatever one comes first to copy it into the output list. Do that until we reach the end of one of the lists, and then copy everything from the other lists over. So if we're merging these 2 lists, we're going to start with pointers pointing at the first element of each list, and we're going to compare which one comes first using the comparator we're given. For this example, we're just using less than and integers for our sorting algorithm. So I'm going to ask, does 1 come before 2? It does, so copy 1 to the output and advance that pointer. Now with just one single comparison, I know that 1 is the first element in my overall output list that will contain all of these elements. I can do that by a lot of transitivity. So 1 comes before 2, and 2 comes before all of these values according to my comparator. And yes, there can be ties, but we're breaking ties arbitrarily, so I'm just not going to be concerned with them. So 1 comes before 2, and 2 comes before all these values, so therefore 1 must come before all of these values. And since this list is already sorted as well, 1 comes before all of these. I know those comparisons have already been made as well. At some point in the recursion, those comparisons have already been made. So with just one single comparison, I'm comparing 1 to just 2, but I've effectively compared 1 to all n elements in these lists. Next, compare whatever is being pointed to. 2 comes before 19. Same argument. If 2 comes before 19, I know it comes before all these values, and I already know it comes before these values. 3 and 19, 4 and 19, 8 and 19, and then I reach the end of one of my lists. Since there's nothing left to compare, I've already compared 19 and decided that it goes after the last element of this list. So then by the same argument, everything that comes after 19 must also come after everything in this list. And these values are already sorted, so let's just copy them all into the output list. So as we went through that, each time I had a value that I was considering and moved it to the output list, to be able to decide the next element of the output list, I at most had to make one comparison. So if our comparison is constant runtime, which it certainly should be, then we have constant time for each element, and we have n elements that we had to decide. So we reach our O of n runtime for merging with this algorithm. And this is what the code looks like. The code looks a little more complex than merge sort itself, but there's not too much logic going on. It's just a lot of bookkeeping for the most part. But I have my left and right side. I'm going to initialize pointers to the first element in each side. And then as long as I don't reach the end of one of the lists, compare the left side and the right side, whatever it's being pointed at, and decide which one is going to make it to the output list. And ties are breaking arbitrarily through the else statement. So the else is going to take care of the ties. So copy that value to the output list, and then increment whatever pointer from the list that we just copied an element from. And then once we reach the end of one list, copy whatever's left in the other list over to the output. So through this is where we finally used our comparator. And in fact, this is the only place we used our comparator in this whole algorithm definition. We took this comparator and used that to compare two values. So with all our type parameter and our function that we took, our comparator, this is the only time we actually used any of that, is right here, when we need to compare two values. This one time inside the merge part of the merge sort. So let's take a look at how this works in the code. And I want to focus on the runtime a little bit and actually visualize how the runtime changes. So I have this code set up, which is going to create a random list of doubles. And I'm going to sort it with some timing code to figure out how long the sorting itself took for this code. I'm going to start by running sort with, and I'm sorting by decreasing absolute value for what it's worth, but just some custom sorting, some custom comparator. And I'm going to call the Scala built-in sort with, and the punchline here is going to be use these built-in sorting methods for whatever language you're using. There have been teams of engineers working for decades optimizing these algorithms and making sure they're correct and everything. Use the built-in sorting methods. So let's run this and see how long it takes. After generating a list of 10,000 elements, how long does it take to sort, for Scala to sort these elements? It takes 29 milliseconds. 10,000 might as well be 0 to a computer. That's a tiny, tiny number. So our goal is to beat 29 seconds. Let's swap this out for our merge sort. Run this. No, it's not going to be 29 seconds. We can even see just how long it took to display the output. It took a while to think. Almost 3 seconds in this. So pretty bad difference there. So let's take a look at our algorithm. This is the same code as we saw in the slides. But there's one really bad thing we're doing here with merge. I shouldn't just say one, but one concept that we're getting wrong. We're doing the same thing we did with selection sort. We have apply, which is horribly costly, it's linear, and we have append, which is horribly costly. This is also linear runtime. So we have a lot of linear runtime inside this thing. So let me swap this out. Instead of calling merge, I'm going to replace this with foreshadow merge. So I'm doing a lot of bad things with my linked lists here. So suppose I didn't. I'm going to have this other method. Does the same thing, same functionality as merge, except I'm being smarter about my lists. I'm using these iterators mostly and a list buffer even to be able to get the same functionality but without doing silly things with my linked lists. And of course foreshadow merge because we'll talk about all this stuff when we get to linked lists. So let's run 10,000. And we get down to a little over 1/10 of a second. So we're doing all right. We're pretty close to that built-in Scala sort. But let's take this a little further. We'll just add a few more zeros, right? So let's sort 1,000,000 elements using Scala's built-in sort. We get 655 milliseconds with the built-in sort. Swap it out for our merge sort. In about 1.5 seconds. So not too much of a blow up in runtime. And this is where the asymptotics help us. As the input keeps growing, we shouldn't have a ridiculous growth in our runtime as that happens. So I'm getting about, a little less, like 2.5 times the speed of the built-in sort. 2.5 times, it's just a constant, so we're not concerned about it in the world of asymptotics. You might be concerned with it outside of that world, so we should still use the built-in methods. But a 2.5 times blow up in runtime, for me, just using a vanilla merge sort that you would find in any textbook, just implementing it verbatim, like this is merge sort, it's just vanilla merge sort, versus that algorithm that engineers have been spending decades of optimizing. 2.5 times, I'll take it. That's not that bad. It's certainly not as bad as the first time we saw when I was messing up my lists, or if we compare this to selection sort, which shouldn't even be in this conversation. Selection sort would be horribly slow for these. I'm in the same ballpark. Like, it's not a terrible implementation because I have the right asymptotic runtime. We're both n log n. N log n is the theoretical bound. You can't do selection. You can't do comparison sort faster than n log n. It's proven to be impossible. And we're using comparators. We have to use comparison sort. So the Scala engineers, however brilliant they are, they're still going to be n log n at best. So we shouldn't expect a ridiculous difference in these runtimes, but we will see a constant difference in these runtimes. So I'm going to learn my mistake from the last lecture and crank this down a bit. 100,000 sounds fine. 100,000 elements. We have our merge sort. I'll switch this back to merge. It doesn't matter too much though. And what I want to do now is set a breakpoint and take a look at how this recursion works. Shift gears into the recursion. I'm done talking about runtime, at least for a long time, for quite a few lectures. But let's talk about this recursion and see how this recursion works. So let's run this in the debugger. Take a look at what's actually going on here. So we've created a list, happens to be size 100,001 because I have an extra element in these things. Create an input of size 100,001, and the very first thing that the very first call does is splits that into two lists of size 50,000 and 50,001. We have this split, and now the algorithm is going to make the first recursive call of merge sort on the left-hand side of that list. So let's step through this thing. It's going to check, is 50,000 less than 2? No, not at all. So split this in half, run the recursive step. Split that into two lists. So I had my input of a list of size 50,000. Split that into two lists of size 25,000. That's my left and right. And then make the recursive call on that left-hand side. We don't have anything to compute. Okay, still greater than 2. Split this in half. Nothing to compute yet, so we're just making recursive calls, splitting the list in half, making a recursive call, splitting the list in half, making a recursive call. And we can start seeing how we're splitting this thing down. With this specific call, we got an input of size 25,000. We split that into two lists of size 12,500. We're going to make that recursive call on the left-hand side of that first 12,500 elements. So at this point, I want to take a look at the stack and see where we actually are in the runtime of this. So in our main method, we're waiting on the only method call, that large example call, which stores my code that's doing this stuff. Large example, this created the list of size 100,001 and is waiting for this call of merge sort to return. Merge sort, that top level call, had a list of size 100,001, split it into two lists, and is waiting on that first recursive call to return. It's sitting there on that first recursive call, just waiting for that stack frame to give it a sorted list of those first 50,000 elements. That stack frame is waiting on the same line of code, but waiting for its left half recursive call to return. And the recursive call that we're currently on is waiting for its left half. It's actually about to call that method and put a new frame on the stack to be able to call that method. So you can see where we're going to keep making these recursive calls until we hit our base case. So I'm going to switch my breakpoint. I'm going to put a breakpoint on the base case, and I'm going to resume the debugger. So it's going to run until we get to the base case, and we'll see what the state of everything is when we get there. So I resume it, and we can see we have a lot more frames on the stack. We have this one where we left off at. Split that list in half, got 6250 on the next call, kept splitting in half, splitting in half, splitting in half, and keep decreasing the size of these lists until we finally get down to these small lists, a list of size 3, a list of size 1. We finally get down to this base case. We have a call, a list of size 1 containing just one element, which in our case happens to be 0.089999115, etc. So we have this one value, and we're just going to return that list. And here we can see the power of that log. We started with a list of size 100,000. 17 frames on the stack later, we have an input of size 1. We went down just 17 calls of dividing this in half, and we went from 100,000 to 1. If it were a million, that was 20 calls. I did a million last lecture, but the debugger gets hung up quite a bit. The debugger has a lot to process with that one. But it's only 20 recursive calls if we started with a million. These numbers don't blow up that fast when we're talking about logs. So with this one, we have an input of size 1. We're just going to return it. And we have our first stack frame actually returning. We go back up to the 16th stack frame. We have our sorted list of the left side, which is just that one element. And we're finally ready to make our first recursive call on the right-hand side. This first recursive call is a list of size 2. We have these two elements that we need sorted. We're going to call that recursive call. That's going to make two more recursive calls that both just return. One more. So now we have right sorted and left sorted. And now our task is to merge them. We're going to call merge and get those two into a list of one element. Watching pointers go isn't the super interesting, most interesting thing, so I'm just going to step over that one. And now in our input of size 3, we have our two sorted lists of size 1 and size 2. Oh, geez, I was panicking. I'm like, that's not sorted. It's because we're sorting by decreasing absolute value. Oh my goodness, I was going to panic there. Our comparator is decreasing absolute value, greater than absolute value. So we have these two lists, one of size 1 and one of size 2, and our task is to merge those. Those are going to be merged. And then in our next call, I think I lost where I was there. Just hit this a bunch of times. So if we skip ahead, like I'm doing here, I got lost in all the recursion. Here we go. Hey, cannot find. Is this worth it? All right, this might not be worth it. But once we start getting the recursive calls, recursive calls returning, we'll start getting to combine those, and then we'll have bigger lists that we're merging until we'll eventually get back to the original call. That's going to have two lists of size 50,000-ish that are already sorted. It merges those and then finally returns that value after all these recursive calls start returning up the recursion. So we've seen a few examples of recursive methods, and we'll see a bunch more, but how do we write these? So I have my suggested approach similar to how I had the suggested approach for the state pattern of writing your API, what are you deferring to your state for? That's going to change with the state of the object. What states do you need? Then what state transitions do you need? And then for each one of those states, implement the API based on what functionality you want. Something similar for recursion. I recommend following these steps. Write your recursive method, assuming that all your recursive calls are already correct, and design your algorithm based on that assumption. Based on my recursion is going to be fine, let's design an algorithm based on that. Write a base case with trivial input-output behavior, and then make sure all your recursive calls get closer to your base case. If you set a recursive method up like this, you should be getting the behavior that you expect. So let's take a look at this in terms of merge sort. When we wrote the original top-level merge sort, we hid some of the details in the merge method itself, but the top-level idea of merge sort is, let's assume that merge sort works. We're going to call merge sort on two lists of half the size of the input. And then if merge sort itself works, which we're going to assume it works, our task is to merge these two lists. So let's write the merge code, merge these two lists that are already sorted. And if everything works out for us, recursion kicks in and it all just works. Next, we add in a base case, which is going to be some trivial input-output behavior. For this, any input of length less than 2. If I have an input list of length 1 or 0, it's already sorted. I can just return it. Very simple, trivial input-output behavior. And then, critically important, make sure that our recursive calls always get closer to the base case. So whenever we make a recursive call to merge sort, we have an input of size n, and we're making the recursive calls of size n over 2. So we're always getting closer to that base case, which is a list of size 1. We're always getting closer because our merge sort calls, our recursive calls, are always on lists that are smaller than the size of the input list. So our recursive calls always eventually are going to reach our base case. It's going to reach a recursive call that can actually return something and then make the rest of the algorithm work. So assume your recursive calls are correct and write everything based on this. If this is, this is the kind of the real benefit, I think, in my opinion at least, of recursive methods is when we're writing the method, we can offload a lot of our processing power, of our brains, of our thought and design power on this assumption. Just assume your recursive calls are correct and write your methods based on that. It offloads a lot of the work that you have to think about. Okay, if my merge sort calls actually do return sorted lists, what task am I left with? Well, I have two sorted lists that I have to merge. It makes it a lot easier to develop that algorithm, to write that algorithm, when we're just assuming that our recursive calls are going to work. And if our recursive calls are not correct, we have some issues somewhere in our design that we'll have to work out. But if all our design is solid, if all these 4 steps are rock solid, it should just work seemingly by magic. It's, of course, not magic. But recursion is one of those things that really can feel like that at times. Finally, add a base case with some trivial input-output behavior. This is usually some trivial input, an empty list, a list of size 1, sort a list of size 1, an empty string. For anagrams, a string of length 1 is its own anagram, just return itself in a list. Inputs of 0 and 1 are typical base cases. Inputs of 1 and 2 for your current lecture question. 1 or 2, you're just going to return 1. Those are the first two values in the Fibonacci sequence. Some trivial input-output behavior. And then we're going to add a conditional. We're going to say if the input is in this base case, just run this base case logic, this very simple logic that we're running for that case. Else, we're going to run our algorithm that makes recursive calls and offload the work onto the recursive calls. And by the way, this is what, I forgot to mention it by name, this is what we call divide and conquer approach. If you heard that phrase before, this is what they're talking about. We divide the problem into smaller pieces and conquer those smaller pieces, then merge those pieces back together. We sometimes call it divide, conquer, and merge, but the merge doesn't sound as fun, so get shortened to just divide and conquer. So once we have our base case and a recursive case that makes recursive calls, the last piece, a critically important piece, is make sure that our recursive calls are always getting closer to our base case. So if, say our base case is 0, we want to make sure that, assuming that we can't have negative inputs, we want to make sure, or that we check for negative inputs in some way. But if our base case is 0 and we have some input of size n, we better make sure that every recursive call we make has a size less than n. It should have a value less than n. We always have to get closer to our base case. If we don't, we're going to get infinite recursion, similar to an infinite loop, a loop that just runs forever. We're going to get infinite recursion, which just puts frames on the stack until you fill up your stack memory and the program crashes. It's going to give you a stack overflow error. If you see stack overflow errors when you're writing recursive methods, it almost always guarantees, it's almost always because you didn't reach your base case. You have some logic where you're just not hitting that base case. So watch for this part of it if you ever see stack overflow. Are my recursive calls always getting closer to the base case? And if you can't spot it by eyeballing it, set that breakpoint, run through your recursion, look at your input, and then that first recursive call, it'll usually jump out at you real quick, that first recursive call compared to your first input, is it closer to your base case or not? Usually it's not going to be, and you'll see the error right away.